Hello, everyone. My name is Huan. I'm currently a research scientist of the University Mohammed bin Zayed University of AI. So today, I'm happy to be here to present Introduction to AI. I try to make this a fun journey as well as try to make it as easy as possible to let you understand what is the AI and the future of AI. So before we start, we take a look at this interesting question. Can AI really think? Here I show example of AlphaGo and Go game. So the Go game is different from other games. It highly requires highly about strategic move, and there's not usually there is not easy to find patterns in the rules. And they're just saying if you take a move randomly of the Go game, it needs more than all the all-time numbers in the universe, which means just take random move won't be a good action, and it highly requires strategic move. So what if AI beat human expert like Lisodo and Koja? Does it think the AI? I mean, the second example I show is also from the Alpha series, from DeepMind as well. So this AI can correctly predict the protein structures, and this led the founders of DeepMind becomes the Nobel Prize last year, win the Nobel Prize. So there's a saying: if even for a short um, protein chain, like only 35 amino acids, and a computer that predicted the energy instability with every nanoseconds, 13 thousands configurations, you need 200 times more than the universe age, meaning this is also a very, very time-consuming, computation-consuming, as well as a hard problem. It needs very strategic prediction. So if an AI can predict the protein structure accurately, can they think? And also, this is a example of automatically pilots, for example, like Tesla. What if an AI drive like a driver, right? And avoid all the obstacles, and as well as human beings recognize all the objects in the road on the road. Does it think? And even take a question, even ask the GPT-5 if you can think, but it doesn't answer. It can think. It says I can reason. That is, I can analyze information, connect ideas, and generate logical conclusions. But I don't think in conscious. If you read all these words, does it think? Actually, it's a sort of like thinking, process, like humans, right? But reading AI can think. So I'll leave this question to you throughout the journey and let you decide whether the AI can think. And actually, there is no clear saying the AI can think or not. So let's look at the AI definition. AI is a science of making machines intelligent, able to perceive, reason, act. But yeah, maybe you can draw a conclusion that it can think, maybe not. Depends on how you define it. So let's dive into narrow AI versus AGI, artificial general intelligence. So narrow AI, as known as weak AI, so it's refers to AI system designed and trained for specific limited task or domains. And artificial general intelligence or strong AI refers to human level cognitive abilities across a wide range of tasks. So for narrow AI, it's specifically built for certain domains or tasks, but general AI is with the human level reasoning thinking as well as can tackle a lot of tasks. So if you think what we have shown before, AlphaFold, AlphaGo, Autopilot, Tesla driver, and ChatGPT. Among those aforementioned AIs, which belongs to AI? Take 3 seconds to think. Maybe you thought like ChatGPT is the general AI, but actually none of them are. ChatGPT may be the closest. It can tackle different, sound, for example, audios, videos, textual data, as well as translation, different tasks, and scholar paper search, etc. But actually, it's still like a narrow AI because you cannot tackle all different kind of tasks, right? It's just still limited to some of the image generation and textual question answering. So there's still a long way to go to AGI. But we see a framework of what AGI works, how AGI works from ChatGPT. So a brief history of AI from symbolism to connectionism. So I'm going to talk about the history of it. And before is like a long time ago, 1970s and 1980s, there's expert systems. It requires human labelers or experts to input knowledge in a database. It requires a lot of like manual work and a lot of rule-based work, like if-then rules. For example, if you find this feature, then it will classify certain disease, for example, or certain type of image it comes from. So there is a very famous system called MySing trying to find a medicine, right? So the patients, we just replace the non-expert users with patients and human experts with doctors. So doctors would would put tons of knowledge into this database, and it will give a hard matching, like if-then rules, to give suggestions to the users. If we dive a little deeper, the system can be classified into consultation system, which is an interface to interact with the users, and we have explanation system, which is trying to find the dynamic database and static database, which dynamic database is contains patient data, context trees, or dynamic data, anything that relate to dynamic environment or from the users or patients. And the static database contains static rules, parameters, properties, context types, and properties tables, etc. So it basically match for example, the patient's features with what is inside the database, the static database, the rules, to give suggestions. They have pros and cons, like for this expert knowledge system. So it has high interpretability. So knowledge is presented in explicit knowledge forms, so it's very explainable. And knowledge engineering dependent. It requires manual input, a lot of like number of rules and knowledge. So manual work. Emphasize on reasoning. So assume that intelligence mainly lies in a logical reasoning ability. It made reasoning also explainable. Lack of perceptual ability cannot effectively handle perceptual data such as image or speech or audio data because those ones are not easily interpreted into and easily tackled inputs. For example, like whether it is more than 60 years old or not, right? So and also it didn't list here, it cannot learn from data. So after that, there are a lot like many data-driven approaches came out. Maybe not after that is concurrent then, but it learned from different perspective. It's not like human manually input some rules. But for example, this is a nearest neighbor comes from the paper nearest neighbor pattern classification from 1967 by Thomas and Peter, these two scientists. So what he does is trying to classify it whether from a cat or dog, for example, class 1, class 2, by finding certain neighbors within certain distance in a feature space. So if it is, you have to define a distance function within for example, like 5 nearest neighbor, then you will just find 5 nearest neighbor of the nodes if whether majority of them belongs to dog or cats. And the second one is based on statistical learning theory, support vector machine, SVM. Is being proposed be widely used in 1980s and 1990s. So what it does is trying to find those closest to this decision boundary, which hasn't been found out, but closer to the other class called separate vectors. So what the algorithm does is trying to find the decision boundary that to split those support vectors, but keep them into a certain distance. It called a margin. So it successfully separated those two classes as well as keep certain margin to find this decision boundary. And lastly is about neural networks. Neural networks is trying to mimic human, what is the neural cells inside our brain. So it called, we talk about the symbolism, right? So this is called a connectionism. So this is a single neuron we talk about. This is the impulse X and the W are the ones we call the weights. So we are trying to make multiplication between the X and W to make an output. So this is a single neuron. We will make thousands of neurons inside, and we will stack them to make neural networks to make the final outputs through backpropagation, but we will talk about it later. So data-driven approach is exemplified by KN's SVM neural networks, learn directly from data to automatically capture complex patterns and representations without explicit rule design. So we already know the neural networks. People starting doing is like stacking Lego blocks. So like firstly in a small house and then tall buildings, later on skyscrapers. So deep learning is a subset of machine learning that use multi-layer neural networks to automatically learn hierarchical representations for data. So why neural networks make a revolution in after 2000s? Because we have much more powerful GPUs, which is computation powers that are very critical for deep learning algorithms work. So here are I show some deep learning networks, deep networks. So first is MLP. So this is a shallow neural network. It's just with multiple neurons, but with a single hidden layer, an input layer, output layer. But what if you stack them more times? It actually gives more freedom for the model to learn complex representations. So this N, usually for MLP, there will be very shallow networks like 4 or 5, usually not more than 10, because if you stack it over 10 layers, it can face a lot of problems like a gradient vanish sort of thing. And later you will see VGG Inception, which is from Google, and ResNet from Microsoft at that time. These three networks are for vision. So for image recognition, for example, image has a larger, space of dimensionality of inputs. So VGG has 16 layers, and Inception V1 has 22 layers, and V4 has 75 layers. You see, there is a trend to stack more layers. And for the ResNet, usually there will be a ResNet 18, 34, 50, or 101 or 152, but there is a very, very deep one. It's up to 1,200 layers. So this is a skip connection. You will see this skip connections try to combine, try to give a shortcuts from the shallow layers to the deeper layers. It gives more, power for the network to stack more. And later on, how much learns? You have the models, but how does it learn? Still take the cat dog classification, for example. We saw this image. It clearly shows it's a cat, right? It is like with the features of the cat eyes as well as the cat ears. But how the computer learns, only see those digits, right? How does the computer make the decision it is a cat? Well, we basically use the three types of learning techniques. One is a supervised learning. So for example, you have the image of a cat, you have a magic function. This magic function directly map the X into Y, which is the label is a cat. What do? It's simply just collect the data of cats, X1, X2, And the non-kiss, which is dog here, like X3 and X4, of course, you can stack in more categories, or you can collect more images within the category. And then you just push those data into this f function to give the answer, focus and let it learn. So one technique is called backpropagation. It's trying to push the network weights, as we mentioned, the W, closer each time to what we desired to classify it correctly for it for every single labels, every single label. And the second technique is called unsupervised learning. So this is a supervised learning we face. For example, like there are two classes, dog and cats. We try to find a decision boundary, which is in the feature space, push the network to understand what is the difference between the cat and dog. But unsupervised learning, what if you don't have the labels, right? As we mentioned, you have to collect the image of cat, collect the image of dogs, but what if you just collect many images, don't know where it's from? So in a feature space, there's a concept called clusters. You can define how many clusters there are. For example, like if there are only two classes you want to classify, and you're sure this images you are trying to classify are only belongs to cat or dog, just define the cluster number into two. Otherwise, you can define more. And here, five, right? So you will also define a distance function. Now you will have an algorithm within a certain function close in a certain distance, sorry. And those points within a cluster are close to each other, belongs to one cluster. Then you will have an unsupervised learning. So it's totally based on the statistical feature of data, not just human labeled labels. And the last one is a reinforcement learning. So reinforcement learning requires an agent, we call it agent, which is the model you have, interact with the environment. So environment will give a state, which is, for example, like a Super Mario, you gave the screenshot of the image to an agent. An agent will, based on this image, for example, whether it is an applicable here to give a jump. If we say it here is A, B, X, Y, which is the direction, and up, down, left, right are the actions you're gonna take to take the action, and the environment will retain a reward for the agent to update itself. Here I provide a short video. You see, if we can make this screenshot into this block world and use neural networks, we can still use neural networks to optimize the whole thing. And your neural network is called policy network. You're trying to give the actions it desire to. So 3 pillars for AI. They are models, which is the models, whether it's a VGG, is a small model, or is a OpenAI large model, or multiple models trying to combine, or anything else. And then AI hardwares. So you need computation powers, GPUs or CPUs to compute. And data, you have to collect a bunch of data, whether it's a supervised learning, the X and Y labels, as well as you collect a bunch of data just for unsupervised learning. Or have to define a simulator or environment or reward function for reinforcement learning. I have to emphasize here the hardware now is more and more important because in a deep learning, there are a lot of like parallel computation. So GPU usually have much more power than CPUs. So usually CPUs is good for sequential computation, but GPU is for parallel computation. We still take the example of cat and dog classification. And we have the function here, which is the model, and we have a bunch of data here, which is data, and we need a GPU for computation. Application social impact. Now, I'm lucky be into one of the project with the hospital that's called fetal ultrasound project. So usually doctors will sit in front of screen and move the probe on a pregnant lady to give an accurate position to give the baby the fetal ultrasound videos. But what if in a low resource area? Like we only have cell phones. We don't have the expensive devices. So we can use what we can do is we can use this prop handheld devices to give a blind scan. For example, there are six trajectories on the belly. And then we will have it called blind scan ultrasound videos. And what we can do here is what we did here, we train it on open data sets, which is with blind scan ultrasound. We test on our totally unseen data sets, which is collected from the hospital. Now we can successfully segment the abdominal area of the baby. And then after that, we can measure how, the healthiness of the baby by measure the abdominal circumferences. Another thing is brain tumor segmentation, which is in brain tumor, usually like people will have four different types of MR, T1CE, which is contrastive, and T2 or flare, which is fast MR. But some of them, like the modalities will be missing. And you see these different colors will represent different types of tumors. So what we did is we corresponded to different types of missing, combinations of missing. For example, like the black dots, meaning the existence of a certain modality, and the white dots means the missing of certain modality. We consistently perform good than existing methods. So this is a die score for segmentation. So for brain tumor, we have a better treatment of whether there's a tumor or there's a type of tumor. And the other applications are embodied AI. Like imagine you have an agent, which is a robot trying to move from point A to point B with a certain language. So what do you do? Here, you will like the robot will face multimodality data like image or videos, and as well as languages, and as well as the robots needs ability to plan. So they're like multimodality as well as planning ability inside. The other applications are AI for science. As I mentioned, the AlphaFold is an AI system developed by DeepMind that predicts 3D protein structures from amino acid sequences with remarkable accuracy. Or there are some AIs for materials discovery or particles or chemical particles prediction, right? A machine learning to predict design and optimize novel materials with desired properties much faster than traditional methods. So future direction of AI. So we are now at the intersection of multimodal representation learning and decision making because we are drained of language data for large language model training. As we know that all of the data, it says all of the data has been used for the training of LLM. Now, a lot of like top labs are trying to find breakthrough point to find more modalities to combine. So Genie 3 is also from Google, a new frontier of world models. So what it does, it has a simulator that to map the whole. For example, this is a Mars field, is a Mars surface, and a Mars rover trying to navigate through the surface of Mars, and it interacts with the environment. It has the real physics inside the world model. And not only in languages, but we can combine a lot of other things. For example, like the spatial sensoring ability of the robots to let it really understand the world. Then we're getting more closer. We're getting much more closer to the AGI. And the second one is decision making, like the robots we now. You see, this is like a video recently from Sharpon robots. This robot working really like humans. And but if you cut, the material through, it only shows their circuits and frameworks inside, which means it's real robots, but it is growing. I mean, evolve really rapidly. The other thing is reasoning model for AI agents. For example, the AI like ChatGPT, the users ask questions to an agent instead of like just give the correct outputs or wrong outputs. It contains reasoning ability, like it called the chain of thinking. So with a multi-turn, which is thinking step by step, you'll give explainability inside from the point A, which is the prompt, to the point B, which is the outputs. It gave much more, lights shed into the model. It's no longer like black box model anymore. So it gave them more ability to understand how the model thinks. And even gives much stronger ability for the model to get the correct answer. It also needs multimodality. It's not only like language model, it can be a large vision language model as well. So it gave more, there are much more things can do with multimodality as well as decision making. So message to wrap up. Today we talk about what is AI, definition of AI, narrow AI versus general AI, a brief history of AI, start from symbolic AI to expert systems to the rise of machine learning, connectionism, and the deep learning revolution, and how machine learning learns, supervised learning, unsupervised, and reinforcement learning, three pillars of AI, applications, future of AI, etc. Thank you.